Lesson 10, Torque, Levers, and Mechanical Advantage. A machine is a device that helps us perform tasks. It is designed to achieve at least one of 5 main functions. Number 1, change energy from one form to another. Example, a light bulb. Number 2, transfer forces. Example, a pulley or a hoist. Number 3, change the direction of the force. Example, a pulley. Number 4, change the magnitude of the force. Example, a hoist. Number 5, change the distance or speed. For example, a ramp or an engine. Simple machines can be categorized into 2 families. The inclined plane family, which includes the inclined plane, the wedge, and the screw, and then the lever family, which includes the simple lever, the pulley, the wheel and axle, and the gears. Let's start by looking at the lever family of machines. This includes the lever, which is a rigid bar that can rotate freely around a support called a fulcrum. The fulcrum is a support around which a lever can rotate. The effort force is the force applied to one part of a lever to move a load at another part. The load force is the force exerted by the load on the lever. It's given the symbol F with the lower subscript L. The effort arm is the perpendicular distance from the fulcrum to the effort force and is given the symbol D with the subscript E. The load arm is the perpendicular distance from the fulcrum to the load force and the symbol is D with the subscript capital L. Levers are divided into 3 classes depending on the position of the load, the effort force, and the fulcrum. The first example is a first-class lever. And we have everyday examples given, such as a hammer that is removing a screw, or a pair of scissors. With each of these, you can see they all share similarities in that the load force and the effort force are separated with the fulcrum in between. Okay? So we have load force, fulcrum, effort force. A second-class lever, the most popular example from everyday life is the wheelbarrow, is one in which the load is between the fulcrum and the effort force. So here we have the fulcrum, then we have the load, then we have the effort. The third class lever, an example would be using a pair of chopsticks. And here it looks similar to the positioning above for the second class lever, but if you look carefully, we have the fulcrum, then we have the effort, and then we have the load. Now take a look at these distances that we've talked about before. The distance between the fulcrum and the load is called the load arm. And is given the symbol DL. The distance between the effort and the fulcrum is called the effort arm. And is given the symbol D capital E. A pulley is a wheel with a grooved rim in which a rope or cable can run. And if you take a look, you still have these same quantities that can be identified and measured within a pulley system. So you do have a fulcrum, you do have an effort force, and you do have a load force. You can also measure the effort arm, which is the distance between the fulcrum and the effort force, as well as the load arm, which is the distance between the fulcrum and the load force. Finally, we have the wheel and axle. A large diameter rigid disc connected to a small diameter rigid rod. And you can see that in this diagram, the wheel and axle are used to perform a task. Gears. Gears are toothed wheels of different diameters linked together to change the speed or direction moved. They are used to accomplish the following things. Number one, to increase speed. A larger tooth wheel connected to a smaller tooth wheel will cause the smaller tooth wheel to rotate faster. We see this in mechanical systems such as automobiles. We also see it in mechanical systems such as analog clocks or watches. Gears can also be used to increase force. A larger toothed wheel will turn slower than the smaller toothed wheel, but with a greater effort force. And finally, gears can be used to change direction. Toothed wheels that are part of a system will rotate in opposite directions. If one toothed wheel is rotating to the right, the adjacent toothed wheel will rotate to the left. Let's start looking at torque and levers. Note that I've put in page references. In the content browser, you can find a reference textbook which will provide you with some additional reading and some additional practice in each of these areas. So feel free to look in the content browser and further your understanding by browsing our reference text. Torque is a quantity in physics, one that you're familiar with, especially if you are familiar with automobiles. It's a measure of the rotational force on a rigid object around an axis or a fulcrum. The symbol for torque is the capital letter T, and the unit of measure is the Newton meter, given the symbol capital N, small m. We can also call it a moment of force. So torque is often called a moment of force. Those two terms are interchangeable. The amount of torque depends on two factors. Number one, the magnitude of the force, F, and number two, the distance between the force and the axis or the fulcrum. And we'll look at examples of each of these. So here we have a force applied at 90 degrees along a lever. This is our lever here. And the distance between the force and the lever can be measured as this distance here, d. You can reduce the distance by placing it closer to the fulcrum. This is our fulcrum. Let me just label it. This is our axis or fulcrum. If the distance between the force and the axiom increases, it makes the job easier. If the distance is decreased, it makes the job more difficult. This is our equation for torque. Torque is equal to force times distance. So remember that, we'll use it often. And what we need to know is that torque increases as force increases. So if you put more force, you'll get more torque. But as the distance decreases, the amount of force required to do the same work will increase. So as the distance decreases, the force must increase. Okay. Let's try an example to help us with our understanding. Calculate the magnitude of torque on the wrench. Let's see what's given in this question. We're given a force of 84 newtons and the distance between the force and the axis is 0.25 meters. In order to calculate the torque, we'll use the equation torque is equal to force times distance. So we have 84 newtons times 0.25 meters. If we punch this into our calculator, we end up with 21 Newton meters. You can put a little dot in there, or you can omit the dot and just write 21 Newton meters. You'll see both in different texts. Okay, so here's a summary of the different classes of levers. The first class, the second class, and the third class. Good for you to review. Next, we have a pair of equations, and these are really helpful. And we use these whenever we're doing calculations with levers. So the torque on levers can be looked at in two different ways. We have the effort torque, and then we have the outcome, which is the load torque. So this is our input, what we are doing, and this is our output, what we get out of it. Okay? Let's try an example, see if we can calculate it. A man uses a first-class lever to move a rock. The effort force has a magnitude of 4.5 times 10 to the power of 2 newtons, and the distance from the fulcrum to the effort force is 2.2 meters. What is the magnitude of the effort torque produced? So we have an effort force is 4.5 times 10 to the power of 2 newtons. And we know that the distance from the fulcrum to the effort force, so the effort arm, is 2.2 meters. And what we want to find is the effort torque. So we know the effort torque is equal to the effort force times the effort arm. That's 4.5 times 10 to the power of 2 newtons times 2.2 meters. If we punch this in, we end up with 9.9 times 10 to the power of 2 Newton meters. If you prefer to write it outside of scientific notation, that is 990 Newton meters. Okay. You can balance a lever when the load force and the effort force cause a lever to balance. We call it static equilibrium. And there's a law of the lever which states that whenever a lever is in static equilibrium, the magnitude of the effort torque equals the magnitude of the load torque. So we know that the effort torque must equal the load torque. So we can write that as an equation. And this is our equation here, which summarizes the law of the lever. Let's try with an example. A camper wants to mount a trailer on blocks for the winter. One corner of the trailer is lifted by applying an effort force using a 3-meter steel bar. Determine the magnitude of the effort force required, and you can ignore the mass of the bar. Let's start by writing down everything that we know that is given in this question. So we are given the load force right here, which is 1.8 times 10 to the power of 3 newtons. And we know that the load arm, this distance right here, between the fulcrum and the load is 0.45 meters. What they want us to find is the effort force, determine the magnitude of the effort force. And what we'll also need to solve this problem is the effort arm. So this distance here, from here to the fulcrum. If we know that the total distance is 3 meters, and we know that this part here is 0.45 meters, then the effort arm must be 3 meters minus 0.45 meters, which is 2.55 meters. In order to solve this, we're going to use the law of the lever, which states that effort torque equals load torque. So FEDE equals FLDL. And what we want to solve for is this guy right here. So we're going to divide both sides by DE. These will cancel each other out. We are left with the effort force is equal to the load force times the load arm divided by the effort arm. We can put in our values here. So we have 1.8 times 10 to the power of 3 newtons. That is our load force times 0.45 meters. That is our load arm divided by our effort arm, which we said has a magnitude of 2.55 meters. So the effort force required to lift this trailer onto the hoist is 3.2 times 10 to the power of 2 newtons. And I want you to keep this in mind. We have a trailer who, in order to lift it, would require a load force of 1.8 times 10 to the power of 3 newtons, 1,803 newtons. But since we are using a lever to do the work, we're using this simple machine to do so, the effort that we have to put in is only a fraction of that. It's 3.2 times 10 to the power of 2 newtons. And the larger this lever is, the smaller this force will be. If you use a large lever, you will get less work required. Okay. A common way to assess the advantage and efficiency of simple machines is to introduce concepts called actual mechanical advantage and ideal mechanical advantage. Machines help us to perform tasks. In doing so, they give us an advantage. For example, if you use a lever to lift a heavy object, the output force or load force achieved can be greater than the input force or effort force required. Another example is an inclined plane. It reduces the effort needed to raise a load to a higher level. For example, whenever we use a ramp to bring an object up to a higher level, it takes less force than is required to actually lift that object up onto that higher level. To determine the force advantage of a machine, we find the ratio of the load force to the effort force. So actual mechanical advantage can be found by finding this ratio, the ratio of the load force over the effort force. Okay, let's try an example. Here we have an effort force of 12 newtons required to lift a load force of 36 newtons. So the actual mechanical advantage we can calculate is equal to the load over the effort, which is 36 newtons divided by 12 newtons. And the actual mechanical advantage is 36 divided by 12. We have an actual mechanical advantage of 3. Okay? Note that if it requires less effort, if this number is smaller, then the actual mechanical advantage will be smaller. Now, the ideal mechanical advantage is another quantity used to assess the efficiency and advantage of machines. In a machine in static equilibrium, or in an ideal or perfect machine, These ratios are equal. However, most machines have some friction due to moving parts, so they're not ideal. They do not transfer energy efficiently. Thus, we can calculate the ideal mechanical advantage using this new equation, which states that the ideal mechanical advantage is equal to the effort arm over the load arm. Let's try an example that has us test both of these equations to identify the advantage and efficiency of these machines. A person jumps onto the end of a plank of a lever. This creates an effort force of 920 newtons, a distance of 1.7 meters from the fulcrum. A smaller person, a load of 460 newtons, located 3.1 meters from the fulcrum, moves a larger distance and rises high enough to perform acrobatic moves. Calculate the actual mechanical advantage and the ideal mechanical advantage. When tackling a question like this that has a lot of information and several parts, it's important to clearly list everything that is given in the equation. So let's start. First, we're given an effort force of 920 newtons. And a distance of 1.7 meters from the plank. So the effort arm is 1.7 meters. Next, we're given a load force of 460 newtons. And the load arm is 3.1 meters from the fulcrum. So with this, we want to calculate the actual mechanical advantage, which states that the load force over the effort force, and we also want to calculate the ideal mechanical advantage, which is the effort arm over the load arm. Okay, it's important to remember or memorize these two equations. Notice that we have L over E and E over L, so L is on the top for the actual and the bottom for this ideal, and similarly the efforts are flipped. Okay, so let's calculate the actual mechanical advantage. That is 460 newtons divided by 920 newtons. If we punch this into our calculator, we get 0.50. Now the ideal mechanical advantage, the effort arm is 1.7 meters and the load arm is 3.1 meters. So our ideal mechanical advantage is 0.55. Notice that for both of these, there's no units involved. These are ratios and you do not need to put a unit in. All right, what you have left to do is some sample practice questions for what we've just studied above. And then when you're done this, I want you to do the corresponding LMS quiz. Good luck.